Okay, next is question number 20. The last question of the May 2023 Physics Unit 1 paper. So it says an actor is wearing a harness. Okay, the harness is connected to a cable and support as shown. Okay, so there is a support. The actor is connected to the support by a harness, by a cable. Okay, so part A is here. It says the force on the cable must not cause the material of the cable to reach its yield point. State what is meant by the yield point of a material. Okay, what is meant by the yield point of a material? Okay, what is the yield point? Yield point is basically it's the stress value at that stress value when a deformed material reaches. Okay, it will undergo sudden increase or sudden change in the deformation, or it will experience sudden deformation, or you can say it will have large plastic deformation at that stress value. Okay, so basically it happens because at the yield point there is some structural, or you can say there is a change in the molecular bonding of the material is happening when it is stressed till the yield point. Okay, so that's why it undergoes a sudden plastic deformation. Okay, so we can say that here what is yield point? uh, the strain of a material at which it undergoes sudden deformation, that is the material experiences what? Large plastic deformation. Okay, the strain of a material at which it undergoes sudden deformation, that is the material experiences large plastic deformation, that is called the yield point of a material. Fine. Okay, next is part B1. The cable and harness are used to accelerate the actor vertically off the ground. Okay, so part B1, it is asking to explain why the forces acting on the actor cause him to accelerate upwards. Okay, so why the actor is accelerating in the upward direction? So to accelerate in the upward direction, definitely the resultant force should be in the upward direction. So how the resultant force is in the upward direction? This is basically what? The tension of the cable, right? So the first point, it is for 2 marks, right? So the first point is what? Tension of the cable acting on the actor is greater than his weight. Okay, so resultant force is in the upward direction, hence acceleration is in the upward direction. That's it. Fine. That's the answer for part B1. Okay, next is part B2. In part B2, the question says The actor has a mass of 77 kg and is lifted vertically from the ground with an acceleration of 2.1 meter per second squared. Okay, show that the tension in the cable is about 920 Newton. Okay, so consider the forces vertically. Okay, the tension, we need to find out the tension. So tension is acting upward, right? If you consider the free body force diagram, this is the actor, this is the tension force, and in the downward direction this is the weight. Okay, so what we can write, T minus the weight is what, 77 g, it is equals to 77 times acceleration is 2.1. okay, resultant force, considering the resultant force in the upward direction. So tension, it is what, it is basically 77 times 2.1 plus 77 times 9.81, so that would give you 917.07 Newton. So we can consider tension, it's what, 920 Newton. That's it. Showed. Okay, so that's the end of part B2. Fine. Okay, next is part B3. Okay, here the question says, to make sure the actor is safe, the stress in the cable must be less than 15% of the yield point stress. The stress in the cable must be less than 15% of the yield point stress. Okay, the cable has a yield point stress of 2.5 times 10 to the power 8 Pascal. The diameter of the cable is 7.6 times 10 inverse 3 meter. Okay, deduce whether it is safe to lift the actor with an acceleration of 2.1 meter per second squared. Okay, so as the actor is accelerated at that rate, that is 2.1 meter per second square, the tension in the cable, it is how much? 917.07 Newton, right? So due to that tension in the cable, let's figure out how much stress it will provide in the cable. Okay, so stress due to the tension T, this is what, this is stress is force over the area of cross section, right? So 917.07 over the area of cross section is how much? We need to find out using the diameter. Okay, so area of cross section, this is basically pi r square or pi d square over 4, right? So pi times 7.6 times 10 inverse 3 pi d squared over 4. So that would give you 7.6 times 10 inverse 3 whole squared over 4. That is basically 1.444 times what, 10 inverse 5. Okay, there is a pi, I missed it out. 10 inverse 5, that much meter square. Okay, okay, so 1 point stress is force over the area of cross section, so let's put it there. Again I missed out the pi, it should be pi times 10 inverse what, 5. So that much. What's the unit for stress? No unit. Stress has no unit. Okay, so 1.44 times pi, 3.1416 times 10 inverse 5. So that would give you, this is in the denominator, and in the numerator there is 917.07 over the answer, which is 1.444 pi times 10 inverse 5. So that is basically 22,15496.7, that much strain. Okay, that much stress. Yeah, stress. Oh, stress, it's not strain. I told it has no units. No, it has a unit, Pascal. Okay, that much Pascal. So we got the acting stress, okay, the effective stress. Now we need to find out how much is 15% of the yield point stress. So limit for stress limit, it is what? 0.15 of the yield point stress. Yield point stress is how much? It is basically 2.5 times 10 to the power 8, that much Pascal. So if you find out, you will get 2.5 times 10 to the power 8 times 0.15. So that would give you 375, and then 5 zeros, 1 2 3 4 5, that much Pascal. So definitely it is pretty much larger than the effective stress, right? So what we can say? So hence it is safe to accelerate the actor at what? 2.1 meter per second squared. Fine. That's what part B3 has asked for. Fine. Okay. Next is part C of question number 20. Okay, here the question says the original cable is now replaced with a new cable made from a different material. Okay, so it is now replaced with a new cable made of a different material. Okay, fine. This material has a lower Young modulus than the material used to make the original one. Okay, original cable. Okay, so the Young modulus of the new cable is less than the Young modulus of the what? Original cable. Okay, the new cable is the same length as the original cable but has a greater diameter. Okay, it has greater diameter, that means it has greater cross-sectional area. Okay, the breaking stress is the same for both the cables. Okay, the breaking stress is the same. Okay, now the question is, explain how the work done to break the new cable is different from the work done to break the original cable. Assume that both materials obey Hooke's law up to the breaking point. Okay, so we need to find out, we need to explain that how the work done to break the new cable, it will be different from the work done to break the original cable. Okay, so let's consider in this case the formula for work done. It's what? Half of F del x. That's what we learned in materials chapter, right? Half of F del x. So to consider the work done to break the new cable, we need to look at the force on the breaking point. Okay, the force that is required to break the cable and the extension that the cable will have at the breaking point. Two things, right? So at first consider the force at the breaking point. Okay, for that the question says what? The new cable is the same length is same, okay, as the original cable but has a greater diameter. Okay, so before that they have said another thing, is that the Young modulus of the new cable is less than the Young modulus of the original cable. So what we know? Young modulus, it is E equals to what? Stress over strain. Sigma over epsilon. Sigma is stress, epsilon is what? Strain. Okay. So since the new cable has lower Young modulus, so what we can say? Stress equals to what? Strain times E, right? So what you will see here, how much is the strain? Strain is 1 over E times stress. So that means for the same applied force, okay, for the same applied force, for the same stress, not the applied force, basically why I'm considering the stress at the breaking stress, that is the breaking point. At the breaking stress, the strain will be what? Smaller or larger? E is lower for the new cable. For the new cable, E is what? Smaller. So epsilon, that would be what? Greater for breaking stress. For what? not for all stress, it is for breaking stress. Okay, breaking stress is same for both, right? So that's why at breaking stress, what strain of the new cable will be what greater. Okay, so if the strain is greater, then definitely extension will be greater because length is the same. So we got extension, right? Extension will be greater. I'm just pointing out like how to approach the answer. I will write the answer after explaining a bit. So del x will be what larger. We got the extension. Now the force. We have deduced that the extension of the new cable will be greater. Fine. Next is what? The force. What we can consider for the force? Breaking stress. Stress equals to what? Stress, it is equals F break. It's the same for both F over area of cross section. So if you consider the force, what you will get? A times breaking stress. So breaking stress is constant. So that means the one which has greater area of cross section will need more force at the point of breaking, right? So that means the new cable has greater diameter, so it has greater cross sectional area. That means it will need more force to be applied to break it. Make sense? So we got that force is also larger, del x is also larger. So let's write it out accordingly. Okay, so the first point for 4 marks, it's for 4 marks. So the first point is what we have deduced from here. Since the new cable has smaller what Young modulus E, so what we got, since it has a smaller Young modulus, so at the breaking point, strain will be what? Reference to this equation, strain will be what? Smaller. Why smaller? Since breaking stress is okay smaller, since I have already used since once. So as what? Breaking stress constant. Okay, first point. Second point is what? Therefore, since what strain will be smaller, therefore what we can say, strain of the new cable is smaller, therefore new cable will have what? Smaller extension at breaking point. Okay, so del x is what? Smaller. Then what? Force. Then for the force, what we have deduced, we are done with the extension. We have deduced that it will have smaller extension. Now for the force at the breaking point, new cable will require more force as it has what? As it has greater cross-sectional area, which refers to which equation? Which refers to this equation. Okay, the more the area of cross section, the more breaking force it will require. Okay, therefore new cable has greater breaking force, right? Breaking force and extension Hence, the new cable will require. Okay, the question was work done, right? Okay, hence the work done, amount of work done to break the new cable will be greater than that of the original cable. That of the original cable. That's it. Fine. So that's exactly 4 points you can write for part C of question number 20. And that's basically the end of the May 2023 Physics Unit 1 paper.